मीठे चावल बनते हैं, इसमें 60 मन खाना बनता है, उसमें 120 मन बनता है। 60 मन मान लो तो 2400 किलो खाना हो गया, और इसका डबल वो है 4800 किलो खाना बनता है। तो लोग पर्सनल मन्नत मांगते हैं, जिनकी मन्नत पूरी होती है वो पर्सनल आगे बनवाता है। छोटी रेक 1 लाख रुपये बनती है कम से कम, और बड़ी रेक 2 लाख रुपये।
Hello, good evening everyone. So today we are at the end of our course. We are here to discuss live session 12 and the exams. We are already done with the course. The course is already over. The assignments are, deadlines are over, and the exam is near. I think it's on 24th April. So today is the last discussion, and if you guys have doubt, you can post in the discussion forum. I'll try to answer them as soon as possible. So let's start with, we are left with 2 weeks assignment, so we'll try to cover them today together. So let's start. So the question is, of the following, the ones which is or are not magic number for atoms to form nanocluster are 24, 55, 140 or 2406. So it has been uh, taught in the class that structure of nanocluster is icosahedral. So the number of atoms which fit this icosahedral geometry will form the nanocluster, and those which do not fit will not form. So we have seen that gold nanoclusters are of AU nanoclusters. They are 25, 55, 140, 2400. So these are the numbers which form gold nanoclusters. So out of these numbers are called magic numbers. Like we had magic number for electronic configuration, or in nuclear chemistry, as we have seen, there is a magic number. So these unique numbers which form icosahedron geometry and then form nanoclusters are also called magic numbers. And these numbers, or these nanoclusters, they follow the free electron model. I'm sure you guys have studied the free electron model in your physics courses or in solid state courses. So these nanoclusters follow the free electron model. Now coming to the question, so the answer here is should be 24 and 2406, because instead of 24 we have 25, and it is 2400 instead of 2406. Okay, so let's move to the next one. The two-photon absorption cross-section for gold nanoclusters and nanoparticles increases with increase in size for nanoclusters, decreases with increase in size for nanoclusters, has similar slopes for nanoclusters and nanoparticles, increases with increase in the size of nanoparticles. So let's see what is the two-photon. Two-photon absorption cross-section for nanoclusters and nanoparticles. So let's draw a graph here. Here is the diameter. Here is the absorption cross-section. Y-axis is absorption cross-section. Now for clusters, it goes like this. So there is AU309, AU149, AU25. So the lines are approximately drawn, it's not from scale, and let me draw for the nanoparticles. So for the nanoparticles it is around 3. So here AU975 2406. So this one is for nanoparticle and this is for clusters. So here we can see that as the diameter is increasing, the absorption cross section is also increasing. So for this the correct answer should be increases with the increase in size for nanoclusters, which is true. This is nanoclusters. As the size in diameter is increasing, the absorption cross section on the y-axis is also increasing. So first option is correct. Then next one, for decreases with decrease in size of nanoclusters. No, as the first option is correct, the second one cannot be because it is opposite. Has similar slopes for nanoclusters and nanoparticles. No, they don't have similar slopes. It seems that they have similar slopes, but it's not drawn on scale, so they don't have. Let me try to put little different slope. They don't have similar slopes. For clusters, absorption cross section increases with increase in diameter and increases with increase in size of nanoparticles. So for nanoparticles also it is true, as the diameter is increasing, the absorption cross section is increasing. Increases with increase in. Here the absorption cross section, it was in the unit of 10 to the power 6 GM. GM stands for the person, but where 1 GM is equals to 10 to the power minus 50 centimeter to the power 4 per second per photon. this guy who got Nobel Prize in 1963 in physics. Okay, so to answer this question, the correct options are A and D, of course, both. So for both clusters and nanoparticles, the absorption cross-section increases as we increase the diameter or the size of the particle. Let's move to the next question. Question 3 is about transient absorption experiments on metal nanoclusters reveal charge transfer time constants of 1 picosecond from HOMO to LUMO, 1 picosecond for core shell, more than 1 nanosecond for HOMO LUMO, and more than 1 nanosecond for core shell. Transient absorption experiments on metal nanoclusters reveal charge transfer time constants of 1 picosecond for HOMO to LUMO, 1 picosecond for core shell, more than 1 nanosecond for HOMO and LUMO, more than 1 nanosecond for core shell. So the answer to this is given by, let me draw the transient absorption graph. So in transient absorption, the y-axis is delta A, delta OB. Here is the time delay in picoseconds. Now this was the signal at which came for 640 nanometer of gold for gold nanoclusters. The fast component was designated to HOMO to LUMO charge transfer in core, and it was 1 picosecond. And this slow component was designated to core shell charge transfer. So this experiment was done. Transient absorption was used to establish that the emission signal is coming from emission is coming from nanoclusters only and not from any impurity. here to answer this question. It is the time constants are 1 picosecond for HOMO to LUMO and more than 1 nanosecond for portion. The correct answer is A and D. Something happened to my pen. It's not writing clearly. Okay, it's working a little better. Okay, let's move to the next question. So the question is, which of the following transitions refer to the bandage transition in the absorption spectrum of semiconductor nanocrystals? One is E2, one is H. E and H means electron and hole. So one is E2, one is 3 by 2 H. One is 3 by 2 E2, one is H. One is 3 by 2 E2, one is 3 by 2 H. So now let's see the absorption spectrum. Wow. My pen is automatically drawing dotted lines. 1.8. This is x-axis is energy in electron volts. This is photon energy in electron volts, and here is the absorption in arbitrary units. So the absorption spectrum for this one is I'm drawing for, it is asking semiconductor nanocrystals. I'm drawing cadmium selenide nanocrystals. So at 2 electron volt there is a peak. So the absorption spectrum looks like this. Oops, it went. There's a peak here and then a shoulder. Okay, so this one is for 1SE to 1S 3 by 2H. This one is for this one is for 1SE to 2S 3 by 2. this peak is for 1p to 1p 3 by 2h, and this last one here is for 1se to 3s 1 by 2h. Okay, so if I'll draw now, in the question it is asked about the bandage. So what is bandage? Bandage absorption is the absorption in lowest energy. So lowest energy absorption is called the bandage absorption. So here we can see it is plotted in the x-axis is the energy, and the lowest energy band is this band, and it is coming from 1se to 1s 3 by 2h. So this one is the bandage absorption. So to answer this question, which of the following transition refers to the bandage transition? It will be 1se to 1s 3 by 2h, the option number B. Okay. If I draw the energy levels, we start from the 1dE, 1PE, and here is 1SE, and here it will be the bandage, that is 1s 3 by 2 holes. Since this part is the valence band part, this is the conduction band part, so it is 1s E, and here we are using H as the uh, substrate. So here this is 1p 3 by 2h, other will be, so this one is 2s 3 by 2, and the next one is 1p 1 by 2. Similarly, two more levels are there. This is 1s 1 by 2h, and this last one is 2p 3 by 2h. H is there in bracket in all the energy levels, which denotes that it is for the holes. That is the valence band. So now the bandage is the lowest energy transition, in which the gap is lowest, like from the valence band to the conduction band, the band which is having the lowest energy. So we can clearly see that from this is conduction band, this is valence band, and the lowest energy transition is here. So this is the bandage. Okay, so this question gets completed here, that for the cadmium selenide nanocrystals, the bandage absorption is 1se to 1s 3 by 2h. So from here to here, it got erased. Okay. Okay, I think the questions are going well. This was the last part of the course which discusses about the plasmonics and the excited state dynamics of these nanoclusters and nanoparticles. So next question is, in the experiment of Rosenthal and co-workers, the first lifetime component T1 in cadmium selenide nanoparticle increases with increase in the size of nanoparticle. Decreases with increase in the size of nanoparticle, independent of the size of nanoparticle, reaches saturation after initial increase in size. So let's start with writing some data. When you will see the decay, I'm not able to draw straight line anymore with this pen. Okay, that's fine. So if we'll see the decay for bigger size nanocrystals, so it goes like this. Maybe this is for 60 angstrom, and when we decrease the size, then we can see a decay like this. So you see the first component gets added. Okay, this is almost the same. Here the there is almost no fast component. Here we see a faster component. Suppose this is for 29 angstrom, and if you will decrease the size further, we'll see a decay like this. So the fast component keeps on increasing. So the fast component is, it's decreasing because uh, the delay is faster. So the fast component is decreasing. Let's write some data. Diameter in angstrom, percent amplitude of the first component, I'm writing only the first component here. So let's write the wavelength for 515. 540, 553, 570, 596, 627. And the diameters taken are 25 angstrom, 29 angstrom, 31, 35, 44, 60. And the percent of amplitude of the fast component which was found was, for the smallest size, it is 69.2%. And as the size increases, the amplitude goes on decreasing. 43.8, 4.2. The amplitude goes on decreasing, but let's see what happens to the fast component, the lifetime itself. So for 25 angstrom diameter, the tau 1 was 3 picosecond. For 29 it is 3.6. For 31 it is 3.9. For 35 it is 4.1. 44 it is 4.3. And for 60 angstrom it becomes 4.6. So as the size increases, the fast component increases. The contribution decreases, but the tau 1 increases. So let's go back to the question. The question is about the first lifetime component increases with increase in the size or decreases with increase in the size. So the answer should be decreases. It's not independent, obviously, because it is changing with the size. Reaches saturation after initial increase with size. So these two options are wrong because it's keep on changing. It's not getting saturated anywhere. So these two options are wrong. Now the first lifetime component, it increases or decreases. So the lifetime component, the component is decreasing, the lifetime is increasing. So it is asking about the first lifetime component, the amplitude. So the amplitude decreases. So the correct answer will be B. As here you can see, it is decreasing. So we can write that as the size increases from 25 angstrom to 60 angstrom, we get two lifetimes, a shorter one 3 to 5 picosecond, which I have shown here, and this is the shorter one, and I have not drawn the faster one. And we also get a longer component. which is around 43.8 to 90.6 picoseconds. I have not uh, written down the longer component in this table. And the second confusion is the percent amplitude of the shorter component decreased from 69.2% to 31.1%. Amplitude of shorter component decreases, which means that the amplitude of longer component increases. Okay. So the longer component will be like 100 minus 69.2, and that will keep on increasing as this component is decreasing. Okay, so we have discussed this question and the answer is B, decreases with the amplitude of first lifetime component decreases with increase in the size of the nanoparticle. Let's move to the next question. The 0.73 picosecond component observed in the experiment of Weiss and co-workers is assigned to phonon-phonon coupling, electron-phonon coupling, electron relaxation, hole relaxation. Now this question is related to this paper Weiss and co-workers ACS Nano 2011 5, page number is 2026 to 2025. So in that paper it has been concluded that the 0.73 picosecond component was due to ultrafast hole relaxation. It is 730 nanosecond or 0.73 picosecond. Is associated with hole relaxation, which takes place in ultrafast time scales, that is in picoseconds. For this they did so many experiments and they took around 21 decays and they fitted it with 5 components with fixed lifetimes. And for the amplitude of the first component, C1, it was initially 0 in the low wavelength range, and then it rises in the longer wavelength range, which is low energy and which is dominated by the holes. So that's how they concluded it. The plot was so when they fitted they found that the C1 component was 0 and then it increased for the longer wavelength range, that is lower energy, and the C5 component, so this is normalized, this is 0 and here it is 1. In the longer component, the fifth component, it showed a plot like this, C5. So the electron, when it relaxes, it comes down in the energy level, and when hole relaxes, it goes up in the energy level. Here it goes to here, it go here, then here. So as the dynamics are opposite, the nature is opposite. So when the hole relaxes, it goes up. So a hole which is in the lower, in this level, will be having more energy than a hole in this level. So it is opposite to the electrons. And further they did experiments which concluded that in higher energy is uh, controlled by the electron dynamics, and lower energy is controlled by hole dynamics. So that's why when they concluded that C1 amplitude is 0 in the low wavelength, that is higher energy, and it is there present in the higher wavelength, that is smaller energy. So this part is dominated by the holes and not by the electrons. So to answer this one, the 0.73 picosecond component, it is assigned to the hole relaxation, not to the electron relaxation, because it occurs in high energy, and this happens in low energy. Okay, let's move to the next question. So the next question is, in the experiment of Price and co-workers, so it is again related with the same paper, the wavelength at which the contribution from both electrons and holes to the total relaxation is equal is 900 nanometers, 1400 nanometers, 1170 nanometer, and 572 nanometer. So we have seen in the previous question that lower wavelength is dominated by electron relaxation, higher wavelength is dominated by hole dynamics. So at what wavelength there is 50-50 contribution from the electrons and holes. So this question is asking at what wavelength contribution is 50-50% from electrons and holes. So there is a formula for this, which is equals to AN NIRE plus now here we need 50-50% contribution this is the chi Ne and chi NH is the contribution of electron and hole to the nth mode of the decay. E or H is contribution of electron and hole in the nth mode of decay. So here we need 50-50% contribution, so it will stay same for all the wavelengths. So when when this equation is solved, we get eta Ne equals to 0.5 An visible by An NIR. So when this ratio is equal to 1, eta Ne is equals to 0.5, which is now C1 is the C1 component is basically ANNIR, because it was 0 in the visible range, it comes only in the longer wavelength. So which remains mostly 0 up to 117 nanometers. So from the spectra you can see it is mostly 0 up to this wavelength. So this wavelength is the inflection point. So here the question asks about at what wavelength the contribution is to the total relaxation is equal. So at this wavelength, which is the inflection point, it is equal. So the answer is 1170 nanometers. So let's see the data at A1, A2, A3, A4, the 5 components, A5. The first is for 572 nanometer. This is the ground state reached in the visible region. So the components are 0, 0.061, 0.12, 0.092, and here 0.73. Now for the absorption in the NIR region, (1170 nanometer), which is our inflection point. Here the components are 0.033, 0.28, 0.26, 0.055, 0.37. Now the ratio of A visible by ANIR, this ratio is what is important, is here 0, here 0.22, here 0.46, 1.7, 2.0. So you see at this wavelength, at 1170, there is contribution from all electron also and hole also. And one more thing is, at the point of crossover, from ultrafast dynamics to whole dynamics, there is significant change in the relative contribution of electron. So if I write the contribution, percentage of electron, so for all the 5 components, the first one will be 0 by 100, second will be 11 by 89, 23 by 77, 85 by 15, 100 by 0. The lifetime, the actual lifetime associated for this will be the frac tau 1, tau 2, tau 3, tau 4, tau 5, all in picoseconds. 0.73, 4.5, 48, 0.70, 12, 46. Here E by H will be the same which I wrote there, that is 0 by 100, 11 by 89, 23 by 77, 85 by 15 and 100 by 0. So what I wrote here is that there is significant change in the relative contribution of electron. So this is the electron contribution, fractional contribution, and there is a change in the contribution when we go from ultrafast dynamics to whole dynamics. So this one is the ultrafast dynamics, this one is the whole dynamics, and for whole dynamics the electron contribution decreases. So that's all in this question. The answer is straightforward, which is 1170 nanometer. The next question is, gold nanoclusters are associated with surface plasmon resonance, icosahedral arrangement of atoms, free electron model, photoluminescence with very high quantum yield. So, gold nanoclusters, as I told in the first question, that they have icosahedral geometry, so option B is correct, and they are associated with the free electron model. So option C is also correct. MSQ question, so both the options are correct. And they are not associated with surface plasmon resonance. Gold nanoparticles shows surface plasmon resonance, but not the nanoclusters. PL with very high quantum yield, they do not show PL with high quantum yield. Their quantum yield is in the order of 10 to the power minus 5, which is very less as compared to other particles. So we cannot say it is high quantum, it is very less quantum. This is also wrong. So for this question, gold nanoclusters are associated with icosahedral geometry and free electron model. Next question is, size dependence of color of nanoparticles is observed when Bohr radius of the exciton is comparable to the radius of the nanoparticle, band gap of the material of the nanoparticle is extremely high, band gap of the material of the nanoparticle is extremely low, or discrete energy levels are present within the band gap. So we see size dependence color, as we all know that the color, the nanoparticles show different colors, different sizes of nanoparticles show different color. For example, gold in bulk it seems yellow color, but the nanoparticle it can be of magenta, violet, it shows different colors. Different sizes show different colors, can be black also. So the origin of colors for these nanoparticles depend upon their size and what happens when they have different size. So the size dependence, the answer is when because of the nano size they have discrete energy levels which is present within the band, and due to different energy levels it's not a band, it's discrete energy level. So due to different energy level, different size can show emission different emission from different levels, and that's why we see different colors. And the second reason is that Bohr radius of the exciton is comparable to the radius of the nanoparticle. So discrete energy levels are present in nanoparticles. So suppose these are the discrete energy level in some size S1. For other size, the energy level will be maybe for this much apart, S2. So when the emission will happen, we can see different colors because these energy levels are different. The energy gaps are different. So due to the presence of discrete energy level, we see size dependent colors. And in the bulk material, what happens? It's a band. There is no discrete energy level, and hence we see only yellow color. Bohr radius of the exciton. Now, what is exciton? It's an electron hole pair which is held by the Coulombic interaction. So, when this distance of the Coulombic interaction is comparable to the size of the nanoparticle, the exciton they can recombine, and then the recombination gives different colors depending upon the size. So these two are the reasons for size dependence color of the nanoparticles. Now the next question is long lifetime obtained for large semiconductor nanoparticles rationalized by considering density of surface traps, solvent effect, intersystem crossing, and oscillator strength. Now for larger semiconductors, the long lifetime is first due to the density of the surface traps, intersystem crossing, and the oscillator strength. Solvent has no role to play over here. A density of surface traps means if there is a on the surface, if there are trap states, it can trap either electron or hole there, and so it may take longer time for recombination. Same is the intersystem crossing. If if the system undergoes intersystem crossing, it may take longer time to come back to the ground state. And the oscillator strength, if there is more absorption, it may undergo longer lifetime. Okay, so for this question, the correct options are first density, and second intersystem crossing, and third is the oscillator strength. So the next question is bi-exciton generation. Bi-exciton generation requires high intensity of pump light, takes place by merger of two excitons, is sometimes followed by emission from S2 state. Depends on the color of the pump. So bi-exciton formation happens when the energy provided is very much greater than the band gap. That is, it is more than the twice of the band gap. Energy of the pulse, that is, photon energy is greater than the twice of the band gap. It will form bi-exciton. So this is color dependent. So answer is, it depends on the color of the pump light. It is decided by the energy, and energy is equals to color, is not equals to color, like it is comparable to color, we can say. So what one energy will be associated with a particular color. So here is the answer will be depends on the color of the pump light. The next question is, bi-excitons can be used to achieve second harmonic generation, saturable absorption, white light generation, and multiplication of number of photons. So bi-exciton is used to achieve multiplication of the photons, because you will use only one photon uh, to form two excitons, and when they will recombine, you will get two photons. So in this sense, there is a multiplication of the photon. It's not second harmonic generation because we will provide higher energy and will get uh, excite the photons of lower energy only, but neither white light generation nor saturable absorption. So it is associated with the multiplication of number of photons. So let's move to the next one. The process or processes involved in the bioexciton formation is or are Auger recombination, singlet fission, impact ionization, and upconversion. So bioexcitons are formed due to Auger recombination, Auger recombination, and impact ionization. So impact ionization is uh, repeatedly we have to pump with high repetition rate is required. So that's why it is also due to impact ionization. So for impact ionization it will be impact ionization will be like this. Here is the excited exciton and then it will form pi-exciton. This is conduction band, this is valence band, this is a hole, this is an electron. So when it will come over here and then again we will give a second pump, it will form this one is the pi-exciton. So this process is called impact ionization. And what happens in Auger recombination is charging. It is charging, discharging. So already this is a bioexciton and when these two will combine, it will provide this electron enough energy to go to the upper energy level. So it will go here and then it will be an exciton. This is the band gap. Eg. So the repetitive process of impact ionization, cooling, Auger recombination and cooling, we get by exciton. So photoexcitation, photoexciton. Excitation, then impact ionization and cooling, then Auger recombination and cooling. So in these process we get bi-exciton. Okay. So the answer will be A and C, Auger recombination and impact ionization. Let's move to the next question. In the experiments of Nozick and co-workers, the efficiency of charge carrier generation is found 100% in lead selenide quantum dots, more in lead selenide quantum dots than bulk lead selenide, equal in both lead selenide quantum dots and bulk, more in bulk lead selenide than lead selenide quantum dots. So the graph between quantum yield versus energy in for this is 100, 150, 200, 250, 300, and energy is in electron volt 2, 4, 6, 8, 10, 12. So for the quantum dots, the efficiency for lead selenide quantum dots, the efficiency is like this. Quantum dots, efficiency of 0.4, and for the bulk goes like this. Obviously you can see that the bulk quantum yield is less, efficiency is 0.2, almost half of the quantum dots. So here the answer should be more in the lead selenide quantum dots than bulk. It's not more in bulk, so this is wrong. It's not equal, it's different. It is more in the quantum dots, more in the lead selenide quantum dots than bulk lead selenide. 100% in quantum dots. Even in the quantum dots, it's not 100%. It is 0.4. That is 40% only. Efficiency of charge carrier generation. We will assume that in quantum dots it should be 100%, but it is not. It is more 40% in quantum dots, then in the bulk but it is not 100%. So that's why quantum dots are used to make solar cells. Okay, so to answer this question, the correct option is B, more in PBSC quantum dot than bulk PBSC. Okay, so we have reached the end of the discussions, and here are some questions which I am leaving for you guys to practice. You can pause the video and try these questions yourself. This is related to the last two lectures of the course, which includes the two-dimensional vibrational spectroscopy. Okay, so that's all for today. So we discussed about the magic numbers in the question 1, that nanoclusters have icosahedral geometry, they follow free electron model, and the two-photon absorption cross-section for whole nanoclusters and nanoparticles. For both, it increases with increase in the size or the diameter. Now, from the transient absorption spectra, the time constant was found to be for HOMO to LUMO 1 picosecond and larger time constants in the range of nanosecond for core shell charge transfer. And the bandage absorption or the bandage emission occurs from 1Se to 2S3 by 2 in the case of cadmium selenide nanocrystals. Bandage is the lowest energy absorption. Then we saw that the first the lifetime the amplitude of the first lifetime component decreases when the size of the cadmium selenide nanoparticle increases. Here's the data showing decrease in the percentage amplitude of the tau 1 component. So simultaneously the tau 2 component amplitude should increase with increase in the diameter or the size. Next, we saw that Weiss and co-workers have concluded in this paper that 0.73 picosecond component is related with the whole relaxation. They have done a lot of experiments regarding this. They have taken 21 decays and fitted it with 5 components. The C1 component is 0 in the lower wavelength, which is higher energy, and it is present in the lower energy side. So thus it is related with the hole dynamics. And when hole relaxes, it goes up in the vibrational. It goes up in the valence band, and when electron relaxes, it comes down. Now, the wavelength at which the contribution from electrons and holes are equal is 1170 nanometer. So this is where the transition happens from electron dynamics to hole dynamics. So next we saw that gold nanoparticles, the terms associated with gold nanoclusters is icosahedron geometry and free electron model. Because they do not show surface plasmon resonance, which is a very good property of nanoparticles, but nanoclusters do not show. And the size dependence color emission for nanoparticles it comes due to Bohr radius is comparable to the Bohr radius of exciton is comparable to the size of the nanoparticles, and there are discrete energy level present within the band. Then we saw there is a long lifetime component in the large size semiconductor nanoparticles which can be assigned due to the density of the trap states, the intersystem crossing, and the oscillator strength. Pi-exciton generation depends upon the color of the pump light, that is the energy. The energy of the pump should be more than 2 times the band gap, or almost 3 times the band gap. The pi-excitons can be used to achieve multiplication of the photons. And the pi-excitons are formed as a result of Auger recombination and impact ionization. And lastly, we saw that in the quantum efficiency of lead selenide quantum dots is more than the bulk lead selenide. In quantum dots it is 40%, but in the bulk it is only 20%. But even in the quantum dots it is not 100%, it is 20% only. So that's why lead selenides are used in the solar cells. So these are some of the questions related to 2D IR spectrum. I'm sure after watching the videos you will be able to answer these. So like this we come to end of the course. Here's a course summary. In the first week we saw the introduction of ultrafast dynamics. We saw the absorption and fluorescence spectrophotometer. We had lab visit in which sir showed you how to record an absorption and emission and excitation spectrum. In the second week, we looked how we calculate the lifetime using the TCSPC instrument, and we learned how to do the data analysis and data fitting of the TCSPC. There was again a lab visit video. In week 3, we looked at how lifetime is measured using femtosecond optical gating, which is more sensitive than TCSPC. There was again a lab visit demonstrating femtosecond optical gating. Then in week 4, we were introduced to pump probe technique, which is most commonly used in the ultrafast spectroscopy. In the week 5, we saw how the ultrashort pulses are produced, how they are amplified, and then we looked at optical parametric amplifications. Then week 6, we discussed about nonlinear optics, in which we saw that for a crystal to show nonlinear optics, it should not have center of symmetry, it should have high chi-square value. Then week 7 was about fluorescence depolarization and its time evolution, basics and application. Then week 8 we saw frosted resonance energy transfer. Then week 9 we had application of ultrafast spectroscopy in basic science, in which we saw how ultrafast spectroscopy can be used to calculate the fastest process, the time taken in the fastest process to happen, which is bond breaking, acid-base reaction, how the ultrafast spectroscopy can be used to decipher the mechanism of acid-base reaction, proton transfer, the time constants related with the processes, excited state dynamics. Then in the week 10th, we saw some solvation dynamics and hydrogen bond dynamics, the proton transfer, inter and intramolecular proton transfers, and we discussed about the famous debate of Takuchi and Tahara. Then week 11th, we saw ultrafast processes in material science in plasmonics. And then in week 12, we saw about the ultrafast dynamics in some nanoparticles and nanoclusters. And lastly, we finished with two-dimensional IR spectroscopy in 2 lectures. So that's how the course finishes, and I wish you very luck with for the exams. I hope you guys will do well. The exam is in online mode. So that's all for this semester. I wish you all the best, and this was Shruti, the TA for the course. The course was Ultrafast Laser Spectroscopy, as you all know, and I think we have done a great job. The course was not easy one, and I wish you all the best.